Hello, everyone. So welcome back. This is the lecture video for day 21. This is the first lecture since exam 2 has taken place. And now we're going to start a new topic. So we're going to talk about regression. This is chapter 4 and chapter 14 in our books. So chapter 4 is the regression part that we covered in Stat 1. So we'll do a review of that today, and then we'll start moving forward in a couple days with the Chapter 14 stuff. So I just wanted to give you an idea of like what we're doing and what we're going to look at here today. So I'm going to pull up today's typed notes, and we can look through those a little bit together, and then I'll do a separate video for the example. So linear regression is just a way of modeling a relationship between two variables. So now I have two variables, and it's my x variable and my y variable. Okay, my x variable is my, here, let me pull it up here, is my predictor variable, and my y is what we call a response variable. Okay, so the way we can choose these two variables, because when we're looking at a problem, reading it, or the data, we should be able to identify which one is x and which one's y. I want to say that x predicts y. So I want to be able to say that my predictor variable can predict my response variable. So when you think about that, then hopefully when you read through a problem, you can pick this out. Okay, so that's the very first thing, because we can't do anything with our data until we can do that. Now, what I want you to think about today, we're going to study simple linear regression. So I shorten that to SLR, and all that means is that I have one y, which is my response variable, and one x, predictor variable. Now, when we get into chapter 14, which is the new material, we will get into multiple x, and that will be called multiple linear regression. So right now we're just reviewing the simple linear regression. Okay, so the first thing we need to do is just identify the x and the y. X predicts y. My predictor variable predicts the response variable. So we can see for an example here that we believe that the weight of a car should be able to predict the miles per gallon. Okay. So once we have that, then here we can get a visual. And of course, that's a little graph, and that's called my scatter plot. What a scatter plot does is a graph of each XY point or pair, and it displays the relationship between X and Y. So you can actually get a good visual of what's going on with my data set just from looking at this. So right here I have some directions for getting my scatter plot, which we're going to do when we look at an example together, but we can interpret the scatter plot. So when we're looking at something like this one right here, you can see that the trend of the dots, it's increasing, right? So as my x is increasing, y is also increasing. That means I have a positive slope. So I can say that there appears to be, now I need to say if it looks strong or moderate or weak. I think this appears to be pretty strong, actually. Positive refers to the slope, if it's positive or negative, and it's a linear relationship between x and y, depending on what those are, right? I would fill those in. I wouldn't just say x and y. I would say, like this one says, husband's age and wife's age. Okay, so that's how we interpret or describe what we see in a scatter plot. Okay. And there's a couple more examples here with the interpretations. Now, I can describe the relationship between x and y without looking at the graph. So without the visual, I can look at what we call the correlation value. This is R. So this is actually a measurement of the strength and direction of the linear relationship. Now, I want you to keep in mind, I keep saying linear relationship, because that's what this is all about. This is about a straight line model. Okay, it's about a straight line relationship. I'm not talking about curved relationships here. I'm talking about a straight line. So every time I say linear, it's just so it reinforces that we're looking at straight lines. Okay. Now I want you to understand R is my linear correlation value. What this means is that it's going to give me a strength of a linear relationship. It's not giving me a strength of any relationship, just the linear relationship. So R might be 0, but we might see that X and Y have a relationship. It just might be a quadratic relationship, right? Like that U-shaped. So it might be a pretty strong relationship, but not linear. So then R would reflect that. I'm going to show you my R scale here in just a minute. So I give you the formula right here for R. It looks big and scary. It's not that bad, but we don't want to do it by hand. We don't need to. So like I said right here, Minitab's going to do this, but as you know, I'd like to show you what Minitab does for us so you get a better understanding of what's going on. Okay? So I don't want to scare you by that calculation. I just like to show it to you. So right down here in the bottom with the reds and oranges and blues, I have my scale. So 0 is in the middle here, and it goes over to the left to -1 and up to the right to +1. Now, a +1 or -1 R value is a perfect linear relationship. So it's a perfect straight line. It means every pair of XY would be in a perfect straight line, okay? So that's rare, right? This is real data. That really shouldn't happen, but it's a scale. So anything moderate we say is between like -0.8 and like -0.5 or 0.4. And on the positive side, +0.5 or 0.4 up to +8 would be moderate. Anything from like -0.4 to +0.4 in the middle here would be considered weak, where 0 is considered no linear correlation. Okay, so I can use that number and kind of interpret the same way as I would the graph, right? So I could say with a Pearson correlation of 0.9, so that would be a strong positive, I would say that I have a strong positive linear relationship between my X and my Y, right? So that would be an example of that. So just using that scale and thinking about what's going on, you could say moderately weak. If you had maybe like a negative like 0.4, maybe you would say it's moderately weak. It's very loose, like it doesn't have to be cut and dry. Okay, so I want you to understand that. And that's my linear correlation value. So it tells me the same thing my graph does, but just with a number and a calculation, where my graph is a visual. Okay, so those interpretations are very similar. So here's some more examples of like the R value. You can see right here, like -1, you can see it's a perfect straight line, right? And what it might look like. Look at down here, this whole bottom line. All my R values are 0 because I don't have a linear relationship, but there's a relationship of some sort going on. There's some shape there, but it's not a linear relationship. So my R is 0, no correlation, no linear correlation. Okay, so that's what I'm just showing you there. The next thing we're going to look at is the least squares regression line. This is my line of best fit. Okay, so the line of best fit has the smallest error, the smallest residuals here. Okay, of course we don't have to calculate this by hand. I'm going to show you a few things. Oops, I need to do that. And but Minitab will do all of this for us. So right here's some information for Minitab, but I want to show you the equation of the line. So right here I have my population equation. So this is yi equals beta1 xi plus beta naught plus epsilon I. All epsilon is, it looks scary, it looks like there's a lot going on. That is just my random error term that is introduced in my population equation. We're not dealing with the population equation because we don't have the population data. We have sample data. But this is what we're going to be estimating, right, by using our sample. So you can see beta1 is the slope, beta naught is my y-intercept. So let's go down here and look at the sample equation. So I'm going to start at the bottom, actually, right here. My algebra equation, y equals mx plus b. We all know that equation. M is the slope and b is the y-intercept, right? So in stat 1, we introduced a new equation, which is very similar. But now it's y hat equals ax plus b. You could see B is still the y-intercept. A now is the notation for my slope. And y hat is my, my response. And what we do that is my predicted, right? Because that's what I'm going to predict, my y. Now here in stat 2, we're going to change the equation just a little bit so it mimics the population equation a little bit more. Y hat equals B1 xi plus B naught. Okay, where B naught is my y-intercept and B1 is the slope. This is getting the equation based on my sample, right? Using my sample. Okay, so you can see the calculations over here on the right. Again, we're not doing this by hand. Minitab will do this for us. I just like to show you. Okay, we may see different orders of this and different symbols, but we should all know what the line of an equation looks like and be able to interpret the different values no matter what we have. All right, so here we're going to look at the standard error. So standard error, we have this also large formula. We don't need that. Minitab's going to give us a standard error. So the standard error represents how much on average the actual values of y, so that means my actual data values that I have, differ from my y hats. So it's calculating this residual right here. So if this blue y is my observed, so it's an actual value, my fitted, which is my predicted, which is on the line, it's the distance here. So it's y minus y hat is my residuals, okay? So that's what my standard error is. It's the average of all those residuals, and you can see the calculation here, and we don't need to do it by hand. We will get it from Minitab, okay? But I just like you guys to see what we're looking at. We're looking at the standard error. So let's get to the equation of in interpreting some values. So I can interpret the slope, right? So here with my slope, I just say for each unit increase in my predictor variable, the response variable will either increase or decrease by the slope value on average, okay? So it's just saying that every time I increase this value in my x, it's going to change my y, right? So that's my slope interpretation. Oh, I keep moving this way too much. And then I can interpret the y-intercept. Now, it doesn't always make sense to interpret the y-intercept, so we just have to be careful of that. So the y-intercept is, as we should know, it's just when x is 0, that's what my y is, right? So that's here's my template for my y-intercept. We have a couple different times when it doesn't make sense to interpret the y-intercept. That's, first of all, if x equals 0 does not make sense for our data value. So if you're talking about height and x is the height of someone when they're 0 inches does not make sense. So we should not be interpreting something like that. The other time we don't like to interpret the y-intercept is if we already have a data value where we have x equals 0. So then we don't really want to interpret it based on our equation because we have an actual data value. So we just kind of keep that in mind when we're interpreting some values. We can use this equation of our line to predict some values. So if you plug an x value into your equation of your line, you will get a y out, right? So we can do that by hand very easily, which we should have done in algebra several times, or we can ask Minitab to do this for us. If we ask Minitab, there's a special button to predict, and I will show you that in the example. Okay. This is just showing you, but I will show you when we get to it. All right, the diagnostics of least squares regression line. What we're talking about here is the coefficient of determination. This is R squared. R squared represents the proportion of variation in my y variable that is being explained by my equation of my line. Okay, so it's how much of my response variable, the variation of that, is being explained by the line. Okay, so if R squared is larger, then it does a good job explaining the spread, and we're talking about the error, the residuals is what's not explained. That's my epsilon in my population equation. course, here I've got some equations. Again, we are not calculating these by hand. You don't need to memorize those or use those. I just like to show you, even though sometimes they look scary. So for simple linear regression, r squared, which is capital R squared, is the same thing as lowercase r squared. Now the difference is that r squared is always my coefficient of determination. It's just for simple linear regression, it's actually my correlation coefficient squared. Okay, so that we talked about before, my lowercase r squared. It's not when we move forward. So that's what it is here. The higher the r squared, the more useful the model is for making predictions. Okay, so we'd like that r squared to be larger, and we really like it to be larger than 75%. I'm going to get to that in just a minute. So how do I interpret my coefficient of determination? So right here, I'm going to say r squared of the variation in my response variable is being explained by the model. That's it. It's a very simple explanation, and you're just talking about the spread or the variation there. Okay, so now getting to know how well my line will fit my data. This is my r squared. This is where I want this r squared to be greater than or equal to 75%. We use that very loosely. It doesn't have to be 75%. It could be like 72%. You can say, you know what, I think that's close enough. I think it's a pretty good fit. But if it's something like 35%, you should not say that's a good fit. You should not say it's good for predicting. And that's what this value tells us. If I should use my equation to predict other y values. Okay, that's what we're looking at when we're looking at the r squared. Okay, so I think that's basically it for the lecture notes. And now I'm going to start a new video to talk about and walk through and equate the example and look at all of those. All right, thank you.